So, I mean, the truth is that triangulations do appear often in many, many different areas of mathematics. You know, don't be surprised when you open the can of soup tonight, you'll see a triangulation there. It is a really, I mean, it's a useful natural object. And one of the areas where this appears very often is in the, let's say, the connections with so-called toric varieties. So it's what algebraic geometers will call baby algebraic geometry. But you know, the theory of toric varieties definitely has a lot of connections. There's, in particular, something called mirror symmetry, which is, one will say, is part of mathematical physics, where this is also, so triangulations and polytopes and all these topics. So these are some interesting applications. And very particularly, there are connections of these two topics with the topic that I'm going to talk today, which is, the last topic is one of the so-called further topics. In the chapter 10 of the book we're writing, calls the topics we have been discussing today further topics, because they don't really, you know, in some sense, we're just giving you a taste of what is out there, but there's a lot to be done. So today I want to talk about lattice points or lattice polytopes and triangulations. Okay, so let me start by defining what I mean by a lattice polytope. So a lattice polytope is a convex polytope, such as, you know, cubes or, you know, this beautiful sonotope, etc., tetrahedron, etc., which has the property that all the vertices are integral. So here is the main definition. A polytope P is a lattice polytope. Some people call just this integral polytope as well. So that's another way. So if I comes through my mouth is to say integral polytope, that's why. Yeah. So lattice polytopes have all the coordinates of the vertices integral. So all vertices have integer coordinates. Okay, so one of the most beautiful results about lattice polytopes is a result that was discovered in the 1950s by a high school teacher in France. So I'm going to state the theorem, and from this theorem I'm going to derive everything today. So this is, in my opinion, one of the most beautiful theorems in mathematics. So it's very, very pretty. The theorem is due to Eugene Erhardt. And this happened in the 50s or something, 60s, you know that. So the theorem says the following. Suppose P is a lattice polytope. And suppose that we define, so let's define, I'm going to define a function that is going to count things inside this polytope. So the counting function I'm going to define is a function that depends on the polytope P and depends on an integer number, non-negative integer number n, and is defined as, it's very simple to define, is the number of lattice points. Lattice point, again, is a point with integer coordinates. The number of lattice points that lie in the intersection of n times a blow-up of P with the integer lattice C to the D. Let's say that this is a P polytope. It's a polytope that lives in dimension D. So this is the famous, this function is called the Erhardt counting function in the honor of Erhardt. So again, let me explain with a cartoon what this means. So this is the most important theorem of today. So I want to make sure that you understand it. So you have a polytope. Let's see. well, okay, I'm going to draw my one polytope here. So let's see, let's draw a square. When I say n times p, so if this is my p, I'm going to dilate. I'm going to extend I'm going to preserve the directions, but I'm going to extend the lengths of the edges by n. For example, if I say 2 times p, what am I going to get? I'm going to get something that is twice as large. You're going to multiply by 2, just like Paco was doing a moment ago, and you're going to get something like this. So this is 2 times p. All right? Everyone understands? So if I say n times p, you get the idea. This is going to be, very big. It's going to keep growing. It's like you're inflating a balloon. This is really the idea. You're inflating a balloon. And, this polytope is inside the n-dimensional space. So inside will contain some lattice points. These blue points represent the lattice points that this set will have inside. And as you blow it up, what is going to happen? The number of lattice points that you have in the blow up is going to increase. It's going to keep growing. More will be inside. And what you have to do to compute this function is exactly, at every stage, you blow it up and you blow it up and you count how many lattice points are there, and that's the function. Okay, is it clear? So this is the Erhard function. And now the theorem says the fantastic thing. This is kind of unexpected, if you want.
Are these only points strictly in the interior?
No, they may be, these are closed polytopes. They may be here, or they may be here. Yeah. So I'm just counting every single lattice point that appears inside P. Yeah? Okay, so now the theorem says that, well, the first part of the theorem, I'm going to put it here, hoping that this will not go away. Don't go away. This is really funny. Anyway, I put a secure thing here. Okay, so the first thing is that this counting function is a polynomial of degree d, where d is the dimension of the polytope. So this is a polynomial. This is a function that can be written as n to the d plus ad minus 1, n to the d minus 1 plus all the way to a0. So this is a polynomial of degree equal to the dimension of the polytope. Yeah, I mean, I said that the polytope is inside d dimensions, so you can say this is inside m dimensions. It doesn't have to be inside the same dimension. So that's the first thing. It's kind of surprising that this function is counting something so beautiful and at the same time so simple kind of shape that the function is going to have. Yes? Yes, this is very much related to Hilbert polynomials, and so this is exactly the Hilbert polynomial of the toric variety. Yeah, so this is definitely very much this is a Hilbert function or Hilbert polynomial. So that's the first thing that he discovered, which is remarkable in my opinion. Then he discovered another thing that is called the reciprocity theorem. So let me explain to you what the reciprocity theorem is, but let me give you some notation here. Let's denote, so if P is a polytope, let's denote by P0, let's denote the interior of P. So if P was this, well, the interior is everything except the boundary, right? This is P0, yeah? Okay? Well, here is a beautiful relation. If you have you can do the same thing, right? You can define the counting function associated to the interior. So you can again say that this is the number of lattice points that I get when I blow up this balloon and I count the lattice points inside this thing. But now I'm counting just the blowing up of the interior. Yeah. So this is a similar thing as that. And now it turns out that there is a beautiful relationship between the counting function of P and the counting function of its interior. They are kind of reciprocal to each other by up to a sign. So this is equal to -1 to the dimension of P times I P0 to the minus. So you're going to evaluate the function in the negative values. Yeah, so these are two remarkable discoveries that Earhart did in the 50s. Now, you may be saying, well, this is very nice mathematics. You know, you're counting lattice points inside polyhedra, but why are you telling me this? This is a course about triangulations. I want my money back. well, first of all, I mean, I think triangulations and Earhart's theorem are connected in a very deep way. Let me start. Okay, before I convince you of that, I'm going to show you a proof of Earhart that to begin with, you need to triangulate. You see, again, you know, the beauty of triangulations is that, well, if I can reduce everything to the case of simplices, I'm done, right? And usually I can do that by thanking, you know, a triangulation. You know, that's kind of the reason why we care about triangulations. But let me show you some examples, because I know many of you may not be familiar with Earhart's theorem here. Let's do some examples. For example, what is the Earhart? Let's do some practice, you know, just for fun. I mean, it's Friday. No, it's not Friday, but it feels like Friday. So suppose I take, you know, just a regular square here. 0, 1, 1, 0, 1, 1. Okay, so let's compute the Earhart polynomial of this thing. So how many? Well, okay, so and I need to count every time I blow up how many lattice points I get. So when I have 2 times, maybe someone will see the pattern and will tell me the answer. This is a little brain aerobics. So you first start with 4. Then when you double it, you get 9. And then when I triple it, how much am I going to get? 16. So can anyone think of a formula? That's okay. So the Earhart polynomial of this polytope will be n plus 1 square, right? Everybody agrees with me? See, there it is. Something of degree 2. You know, it's an innocent example, but it's very illustrative. Okay, let's get a little bit more serious here. How about the cube? So suppose okay, this is a 2-dimensional cube. So we did the cube. So what do you think is going to be a 3 cube, for example? Yeah, it is n plus 1 cube. So n plus 1 cube will be the Earhart polynomial of this guy. And in general, for the d-dimensional cube, you're going to have n plus 1 to the d. That's the Earhart polynomial, which, to make Mike happy the last day, has binomial coefficients, the Pascal triangle as in the coordinates. Yeah. All right. Well, but I mean, the problem in some sense, I mean, there is a real problem going on here. I mean, these were just toy examples. This is easy to see the pattern. But I'm gonna give you a challenge, a real challenge here, and I did not put the answer on purpose. Suppose, you know, your landlord comes to your door. You know, he's an educated man. Says, well, okay, I'm gonna throw you off the premises unless you tell me the Earhart polynomial of the following. Well, I mean, perhaps he's a nice guy because this is an easy problem. Still, so let's see. This is a. I'm going to give you a pentagon here. So it's a pentagon with interior coordinates, of course, which you see in your notes, by the way. You don't need to wait for me to make the picture. So there it is. Now I just need to draw it. Yeah, so here is the origin, by the way. So this is 0, 0. And this is, -1, -1, etc. So that's a pentagon. You can check, unless I did the picture wrong, that this has, 12 lattice points. Count them on my picture or count them by 12 points. 12 lattice points. So what we expect is to know how many lattice points are there in general. Right? Or we want to, so what I wish to know is what is a formula for the Erhard polynomial of this polytope. So I want to know if this is my P. So my wish to Santa Claus is that, what is IP of n? I want a formula. What degree is it? 2. Degree 2. Very good. So it's a degree 2 polynomial. So it has, well, let's see. Can anyone guess what is going to be the constant coefficient? Let's start from there. Just to get you started. It's going to be 1. Good, because the constant coefficient is when we evaluate the Erhard polynomial when in the zero dilation. What is the zero dilation? You shrink the point to the origin. So that means that this is going to be, the last thing should be a 1. Good. So what is the thing in front of it? Well, it turns out, here's a beautiful fact, which also Erhard observed. The thing that goes in front of the leading coefficient is the volume of the polytope. So in this case, the volume of a polytope like this can be computed by, here is where triangulations come again, you see? The volume can be deduced from a triangulation, because you compute a triangulation, add up the volumes of the simplices of the triangulation, and voila. Right? So in this case, it's 17 halves. You can check, what you have to do to compute this number, of course, you just have to break this into triangles that have, area 1/2. And if I did it right, there should be 17 triangles here. Okay, you want me to count? Let's see, 1, 2, 3, 4, 5, 6, 7, 8, 10, 11, 12, 13, 14, 15, 16, and 17. And each one of these triangles has area 1/2. So that's why you have this coefficient there. Now the middle coefficient has also been is understood. It has to do with the area of the thing. Well, the area counted in terms of the lattice points that are inside the boundary. So the second middle coefficient will be 5/2. Yes, Francis.
Will the odd degree terms always have positive coordinates?
Will the odd degrees? What do you mean? These odd degrees?
Oh, like the coefficient of the n.
Yeah, this one.
Yeah.
Well, this one is positive because it can be interpreted in terms of an area.
Right. I guess I was just wondering. Yeah. Right. I guess I was just wondering because of the second condition that if the -1 is introduced in order for the thing to be
Yes. Yeah, so what happens is that this guy will, the first and the second will be positive because they can be interpreted as sums of volumes or areas. They don't all have, the other coefficients will not necessarily be positive. In fact, it's interesting to know what's going on with the coefficients, with the signs of the coefficients. And in general, there is an open question to understand what's going on with the coefficients of these polynomials. But I'm just hinting already that, you see, if you look at this triangulation, right away I can determine the first the leading coefficient, you see? David, you had another question, I think.
Yeah, but I'm
All right. I love those questions. They figured out. Okay. So you have these, and so let me just leave it here as a, I love to give open problems. So one of the big issues going on here is what is the meaning of the coefficients, or what are the meanings of the coefficients of n d minus 2, n d minus 3, etc. There's essentially 3 coefficients that people know answers, more or less, but I'm not going to go into more details. It's an interesting, hot area of research. A lot of people in this room like it. Okay, but my duty here is, as I said, you guys are going to ask your money back if I don't tell you about triangulations, and this does have to do with triangulations in a very deep way, in my opinion. So first of all, I'm going to give you the sketch of the proof of Earhart's theorem using triangulations. I mean, yeah, so in general, the 5/2 is counting the surface is the sum of the perimeter. In this case, is the perimeter. For this particular example, is the perimeter. For a d-dimensional example, in general, will be the sum of the volumes of the surface, the bounding faces. But they have to be calculated with respect to the lattices that they are. You look at the affine span of that face, you compute the lattice, and then that gives you the volume number. All right. So I want to talk about an idea of how you can possibly prove this theorem, or it's like the heuristic of this. So I'm going to call it a taste. It's just a taste of how you prove this beautiful theorem. So this deserves a happy face. Okay, so the idea is the following. You are going to triangulate. So you're going to triangulate the polytope. This is your polytope, and you're going to triangulate possibly using, you're forced to use only lattice points as vertices. It's not legal to use vertices that are not rational. And say you get a triangulation like the one I'm going to draw here. All right? Oops, not a triangulation yet. Now it's a triangulation. Now, suppose we want to count the number of lattice points on this polytope. I claim that there is a natural way of decomposing the polytope into the open simplices in such a way that you can get the total. So then I claim that the number of lattice points inside this figure is equal to the number of lattice points inside the. Let's use colors. So I'm going to call this. Let's call this orange. So this orange means open triangle. So you take the open triangles. Yeah. So you take something like this. How many open triangles do we have? We have 1, 2, 3, 4, 5, 6. So we have 7. I did it. That reminds me of a joke. Remind me of telling you the joke at the end. Anyway. So that's the. Yeah, you understand? I'm just taking the interior. I'm not taking the boundary. Yes? So the number of lattice points here is equal to the number of lattice points there plus the number of lattice points on the skeleton. Yeah, so let me just draw the skeleton. Without the vertices, just the edges. It's easy to get confused in this picture. So those are the edges of this triangulation, you see? Just the edges. And then finally, you have to put plus. This is plus the vertices. So you have so the number of lattice points here can be broken the number of lattice points here plus the number of lattice points in these pieces plus the number of lattice points in these pieces. Yes? Does that make sense? So I can, in other words, what I'm claiming is that the Ehrhart polynomial, and this is valid also for the dilations, by the way. When you're dilating this thing, it's still going to be true, right? So the Ehrhart polynomial of Pn can be written as a sum. So given a triangulation, so you see life begins with a triangulation. Given a triangulation, gamma, whose vertices are integer points, the Ehrhart polynomial of this can be written as the Ehrhart polynomial, the sum of the Ehrhart polynomials of the interior of the faces. Now look, I use I shouldn't use the star, I should use circle, right? Circle is the interior of the face, where I do this for every face that belongs to my triangulation gamma. Let's say I only skip f when it is the empty set, but every other face has to be added there. Right?
Isn't the whole set considered the face as well?
Okay, fair enough. You're right. I should exclude that too. So f different from p. Thank you. Yeah. So let's do it that way. Yeah.
Right.
Oh, that's right. So p is not a face of a triangulation, so I'm safe. Thanks. That's right. Okay. So this equation. What does this equation buy me? That I can prove, if I can prove Ehrhart's theorem for simplices, I'm happy, right? So all I have to do in some sense, you see, triangulation simplify your life. All you have to do is prove theorems for simplices. And this is a common trick in polytope theory. Sometimes you need to find the right triangulation. Yes?
It's not quite made it hard to do without.
No, I'm cheating. I said this is just a taste. Yes, you're right. It does?
A little more thinking.
Yeah, well.
Triangulation still saves your life.
It is, you see. All right. But OK, so how am I going to do it to make a long story short, I'm going to tell you my grandma's recipe for getting the polynomial of a simplex. That's all. All right? So what does my grandma tell me? OK. Here's really a cooking recipe, you know. So here's a cooking recipe to get the Ehrhart polynomial of an integral simplex. So let's say that your integral simplex has coordinates or corners a1, a2, ad. Say, yeah. Say your simplex is maybe a triangle. In this case, d is equal to 2. No, I'm sorry. So I wanna go from 0 maybe. Now it's better. All right, so what do I want to do now? Yeah, so what I want to do now is, so the cooking recipe. So the cooking recipe is as follows. Take your simplex. Here's your simplex that lives in dimension d. Now you're going to put it in one dimension higher in a cone. You're going to make a cone. So the way it goes in this example, so make a cone out of it. Make a cone by so this is dimension d. You can put it in dimension, you're going to embed this into dimension rd plus 1. Yeah? And you put it in the plane of level 1. So this will be in the plane with coordinates. So put the simplex So put the simplex at level at the hyperplane x d plus 1 equals 1. So this is the hyperplane where the last coordinate has a 1 coordinate. So now your simplex is going to look like this, right? So you're going to have the simplex, which is a triangle in this plane. Yeah, everybody sees that? And now I'm going to consider the cone, which is given by these rays. So this, I have A1, A2, A0, A1, A2 in this case. And that gives me an infinite cone. That's like my finger sticking out to infinity. Yeah? Everybody's clear on this? Okay. So, and now here comes the, we have been talking about sonotopes and stuff like that, right? Well, we're going to consider the parallelepiped that these three vectors give you. So what is the parallelepiped? Well, it's exactly all possible sums you can make out of these vectors and shortenings of these vectors. So the parallelepiped is a great word for spelling bees. Parallelepiped. So name of a parallelepiped has to be pi. Is the set of all x's such that x can be written as, lambda 0 a0 plus lambda 1 a1 plus lambda d ad, and lambda is between 0 and less than 1. Lambda I is between. So this is the open parallelepiped. The open parallelepiped that you can construct with these vectors that I told you. So how does it look? For example, if you have a parallelepiped where the vectors are like this, perpendicular, almost perpendicular to each other, you get a cube, right? So parallelepiped is a deformed cube. It's a sonotope here. Okay. So anyway, so the cooking recipe is the following. So this parallelepiped is gonna, be here. Imagine here's the parallelepiped, and all I need to do to get the polynomial that I need is to count how many lattice points are at each level of this parallelepiped, from level 0 to level d. So here is the ending of the cooking recipe. So the way I do it, I denote by delta I is the number of lattice points of level I inside the parallelepiped pi. Yeah, so level I mean is level 1 is those that have last coordinate 1. Level 2 is those that have last coordinate 2, and so on and so forth. All right? All right. So finally, here comes the punchline. You mix all these ingredients, let it boil for 30 minutes, and then the formula, so the Ehrhart polynomial of this simplex. What did I call the simplex? I never gave it a name. What a shame. Okay, let's call it sigma. Now that guy is called sigma. Yeah, so the Ehrhart polynomial of sigma in terms of n is, sum from I equals 0 to d of delta I, and then it's n minus I plus d, choose d. So you can write it in terms of binomial coefficients to make Mike even more happy today. Yeah, so we are being followed here. So there it is. So that's the formula, and essentially, okay, I know that David is not going to be happy maybe, but if you believe the second part and some kind of induction, you can plug it in there, and you get the polynomial for the whole thing, thanks to the triangulation. Chris, someone was going to ask me a question, no? Someone raised their hand here. No? Hallucinations. Okay, so that's the Ehrhart polynomial, and you see, to prove the theorem, you reduce it to simplices, and again, you use triangulations, but, and this is kind of the moment where maybe I'm going to finally say something new for Matthias, is that triangulations have an even deeper relationship with Ehrhart polynomials. And to show you this deeper relationship, I'm going to define what I mean by a unimodular triangulation. So definition. Given a polytope P, by the way, every time I say a polytope, I should just mean a lattice polytope, okay? Lattice polytopes here. A triangulation of P is unimodular. Some other people call it primitive, but I don't know. That's not in this neighborhood, you know. We call it unimodular here in California. If the volume of the maximal dimensional simplices is 1 over d factorials, or yeah, okay. Well, let's say the maximal d-dimensional simplices. Suppose d is the maximal dimension. Okay. So these are what I think, I don't know who talked about this, but I know someone talked about these normalized volumes. Francis talked about normalized volumes. Okay. Okay, so let's do some examples of normalized unimodular triangulations. So the first example that I can give you is, voila, here's one. It's a unimodular triangulation because all the triangles that are involved in this have volume 1/2. Okay. Maybe I should give you yet again the same example that Francis gave yesterday of a non-unimodular triangulation of the cube. So you take the cube, of course, the regular cube, you know, and again you do the same business here. So that's the triangulation that is not unimodular. Who's failing here? Does anyone remember besides Francis?
The middle.
The guy in the middle.
Yeah.
This guy is fat. He has volume 2 over 3 factorial. Well, 1. So this guy is the fat guy. That is not gonna spoil the party. Yeah. So why do I care about unimodular triangulations? Now here comes kind of the punchline. If you have a unimodular triangulation, I mean, from any triangulation, if you use my grandmother's recipe, you can get the Ehrhart polynomial. But why bother, you know? I mean, this is an old-fashioned recipe. We want a low-fat recipe, you know, we're in modern times. So we use unimodular triangulations. If you are lucky and you can find a unimodular triangulation, then you can write the Ehrhart polynomial just straight off the triangulation. Well, you know. So theorem. So if you have a unimodular triangulation, if the polytope has a unimodular triangulation, if P has a unimodular triangulation, let's give it a name because we need that. Let's call it T. Then the Ehrhart polynomial of P is completely determined by the F vector of the triangulation. It's completely determined by the f vector. Who remembers what's the f vector?
It's just how many simplices.
How many simplices of each dimension? Very good. Then the f vector of t. Of t. Which is, again, let me repeat it, is the f1 is the number of edges, f0 is the number of vertices, and so on and so forth, right? Yeah, so yeah, sure. So let me tell you why. So, well, actually, one can even say that this is conversely the case, because if you know the f vector, sorry, if you know the Ehrhart polynomial, and you know there's a unimolar triangulation, you can probably just rearrange things and figure out who was the f vector. But let's just write the theorem this way. Yeah, so all I have to tell you is how does the shape of the Ehrhart polynomial looks in this example, in this situation? Well, it turns out that the Ehrhart polynomial of P can be written as, the sum from j equals 0 to n, to d, because it's a d-dimensional simplicial complex. Fj of t times minus 1 to the j times the Ehrhart polynomial times the Ehrhart polynomial of what? Times the Ehrhart polynomial of, let me just write it as sigma j. So sigma j is a j-dimensional unimodular simplex. And that has a very simple formula. I'm not going to write it. It's just in terms of binomial coefficients that only depends on j, n, and d. So just trust me. I'm not going to write it because it's not going to be very educational. But this is just, so in other words, this formula, this thing here, depends on n, d, and j only. So the only thing that's really changing is the f vector. All right. Now, well, of course, now everybody wants to buy the stock market in a company that sells unimodular triangulations, don't you? Right? I mean, it's kind of the hottest thing you can do, because if you can, you can produce unimodular triangulations of polytopes at demand. You know the Ehrhart polynomial. I have bad news for you. Well, the bad news is that there are lattice polytopes that don't have unimodular triangulations. And here is one of them. Stare at it. The fat simplex. This guy has no unimodular triangulations. How are you going to triangulate that guy? There's nothing inside that you can use to do it. And this guy is already not unimodular, so what are you going to do? Nothing. You have no choice, no hope. So, okay. So that's the sad news. So sad news. Still, even though it's such a beautiful result that you can just express the Ehrhart polynomial, the coefficients, the signs, everything, Matthias, yes. In terms of the f vector of the unimodular triangulation, that's what you care, right? The sad news is that, sad news, not every polytope has unimodular triangulations. Okay, but I like the way that Hollywood ends the movies. Hollywood will never end a movie with such a sad note, and I'm just like that. There is hope. Yeah, then suddenly you hear the Lone Ranger coming. Dun, 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 dun. Yeah, exactly. So now here is the great news. There is a theorem. So this is a theorem, and all the algebraic geometers are going to cheer due to Mumford. Oh yeah, Mumford. I told you it's the Lone Ranger who's coming now. Well, it's actually Mumford et al. So it's not the Lone Ranger. It's the It's the General Custer coming. So the theorem says the following. Okay, maybe your polytope does not have a unimolar triangulation. But if you take the balloon and inflate it enough times, it does have a unimolar triangulation. So given a polytope, a lattice polytope, okay, a lattice polytope. A lattice polytope P, there exists, and this is the situation. There exists a constant that depends on P, so that I'm going to just, this is K of P, but I'm just going to call it K because we're friends. So such that Kp has a unimolar triangulation. So remember, unimolar triangulations, you are allowed to use vertices, integer vertices that are in the boundary or in the interior of the polytope, not only the vertices themselves, okay? So you blow it up enough times, and then suddenly you have enough lattice points to make the trick. All right? Well, aha. He is already bringing up the thing. What's going on with K? Is K an irrational number? Is K, what is it, you know? What is K? What's going on? Well, first of all, there's bad news. The K that is, okay, well, I told you, life is not perfect. Okay, so if you take K, K depends on P in general. Yes? So one of the fascinating open problems, yet another open problem is, can someone figure out a K that works for every P that belongs to dimension D? So take any D-dimensional polytope, maybe, you know, Paco can say, hey, if you multiply by 42, you can always triangulate it with unimolar triangulations. So that's the big open question. So is there a K that depends only on the dimension of the polytope, not just on the polytope? On the ambience dimension?
If we're given P, do we know how to find K?
That's another open problem. Find the computation, well, okay. Actually, Monfort and et al., I think they have an algorithm in the paper. So, but I mean, find an efficient algorithm to find the K, you know. Let's be a computer scientist again and say, find the K. Yeah.
Once you found the K that works, does any higher K?
That's another question, yes. So is it true that if suppose that Paco says 42 works, I swear. Okay, I trust you. Is it true that 43 works? No one knows.
That seems like one to ask, but what about Luiso? Does 84 work? Do multiples of K always work?
Yes, that much is known. Yeah, multiples of the same K, yeah. Have you seen the movie already? No. I'm just kidding. Yes, if you take integer multiples of that K, yes, you're guaranteed to work. But, yes?
What's the smallest D that's open?
D equals 3. No. Because, I mean, D equals 2 is solved because okay, here is the fact. So you compare. In dimension 2, every integer or lattice polygon has a unimolar triangulation. Prove it. It's a beautiful exercise. No. That's just for simplices. It doesn't extend to. Yeah. So yeah, there is something known about in the D equals 3 case in dimension 3. There is a recent paper that shows that for simplices, 4 is enough. The title of the paper is, it's simplices. Anyway, well, we'll talk about it. Well, maybe D equals 4. But D equals 4 for sure is open. And in D equals 3, one thing I can tell you, they know that if you multiply by 4, then you can have a unimolar triangulation. But they don't know whether if you multiply by 5, you can get a unimolar triangulation. Already in dimension 3, that question is open. Sorry? That's what I think. He thinks it's for all polytopes. I don't think so, but I'm not going to fight for him about it. You know? Okay, so just the theorem is that every lattice polygon, you know, and here is the example. You know, what I mean, proof by example. Every lattice polygon has a unimodular triangulation. Gee, I thought I was not going to fill an hour. I know I did, but I'm still going to fill an hour. Okay, that was page number 3, and I don't find number 4, so maybe I won't fill an hour. Yeah, no, here it is, number 3. Yeah, so for example, just for the taste of it, I'm going to dedicate this to Matthias, my friend Matthias, that likes Ehrhart polynomials a lot. For example, if you know a unimodular triangulation of a 3-dimensional polytope, so let's say here's just an example of the theorem that I was mentioning there a moment ago. Where is it? Here is the theorem. So this is an example of this theorem. So example. So suppose you have P. So T is a triangulation of a 3-dimensional polytope. Then you can write in terms of the F vector the coefficients. And that turns out to be 1 plus F1 plus 3, minus 3 halves F squared plus 2F3. That's what is going to multiply N. So sorry, I should write here IPN, right? This is the formula for the Ehrhart polynomial of this polytope in terms of the F vector plus the F2 over 2 minus F3 and square plus the volume of P times N cubed. You see? So if you know the triangulation, you can play the game of understand. If you want to, if your business is to try to understand the coefficients of the Ehrhart polynomial, you may want to look at these things because they do look related to the phase lattices of phase F vectors of triangulations a lot. I will close stating another really cool open conjecture on triangulations that has to do with Ehrhart polynomials. All right. Yes?
The volume of P is free, essentially, right? Because the triangulation is involved.
The volume of P is what, sorry?
F3
Oh, yeah, it's thanks.
divided by 6, I guess.
F3 divided by 6. That's right. Okay. How many people have heard of Hilbert? Good. Just checking, you know. All right. So Hilbert, as you know, he proposed some famous problems in 1900, and no one is going to leave the room until you tell me who were the 23 problems. I'm just kidding. No. Problem number 3 is one that is very close to what I'm going to tell you. So I want to remind you of what that says. Suppose, so Hilbert asked the following question. So Hilbert's first problem is the following. So suppose, P and Q are polyhedra, are three-dimensional polyhedra. of the same volume. All right? Is it true that I can chop off P? Chop, 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 chop. I take knife and scissors and chop it off into pieces, and then I rearrange the pieces and I get Q. Yeah? So this is called, yeah, so suppose this is P, and then I chop it off, cut it like this. In fact, you can think this is a triangulation, really, without loss of generality. So you triangulate it in some way by adding some enough points. And if this is P, you cut the pieces and imagine that it's a jigsaw puzzle. And then you rearrange it and then you get Q. This is Q. Is it true or false? Yeah. Two things have the same volume. You can chop off one, rearrange it, you get the other one. Well, the answer is false, because Max Dehn answered the question. So Max Dehn, which I think he has more fame because of his work in topology, solved this problem by giving an example of a cube and a tetrahedron that had the same volume, and that yet you cannot possibly chop off one and get the other. Okay? Just so that you know. But in dimension 2, this is true, by the way. I mean, that's why Hilbert was asking this question, because he knew that in dimension 2, this was true. So this theorem, if you replace, so this is true for dimension 2. And this was proved by the father of the inventor of non-Euclidean geometry. Well, one of the inventors of non-Euclidean geometry, Bolyai, from Hungary. So his father proved that this thing, if you have two polygons in the plane that they have the same area, you can chop off one and get the other. Chop it off, rearrange the pieces, and you get the other one. Okay? Is it clear? Good. Okay, now I'm going to generalize Hilbert's third problem. Okay? So this is Hilbert's third problem. Now I'm going to state Greenberg's first problem, or Greenberg's problem. So Peter Greenberg was an American mathematician who died very young, but he managed to prove the following thing. Peter Greenberg. So he proved that if two lattice polygons have the same Erhard polynomial, then you can find a triangulation of one that you can cut through the triangles. You cut, rearrange, and you get the other. Let's call P and Q. Then there is triangulation, or yeah, I can write it more formally. There's two triangulations, one of P, one of Q, and there is a unimodular map between them, something like this. So let me write more formally. I don't have to be so sloppy. Then there are two triangulations. So T of P and T of Q, such that, and there is a map between these triangulations such that the number of lattice points in sigma is a simplex inside the triangulation of P is equal to the number of lattice points in phi of sigma, which is the other triangulation. So there is a matching of the triangles, and phi is actually phi is continuous, and piecewise linear. It's like it's a very big generalization of the theorem of Bolyai. Not just for volumes, but for lattice, kind of respecting the lattices.
And I guess also phi precise volume everywhere. Is that the
Yeah. So yeah.
But they're not rigid motions.
No, they're not rigid motions piecewise, but they are unimodular. They're linear transformations, linear unimodular transformations. So piecewise, this is piecewise linear unimodular. And preserves volume, preserves volume.
But Bolyai's theorem, was that for rigid motions
Yes,
and polygonal pieces?
for rigid motions, polygonal pieces. Okay, so then the conjecture is the following: Can you become Max Dehn? Max Dehn gave a counterexample for the three-dimensional thing of the volume. Can you give a counterexample to the three-dimensional analog of Greenberg's theorem? That will be, so that's, so let me just end by writing that conjecture, and then I end. So, question. Can you prove or disprove? Or disprove a 3D analog of Greenberg's theorem. Okay, like for those of you, okay, as Jim Morrison used to say, this is the end, my friend. Thank you so much for everything. In the name of my co-organizers, thanks for your patience and your endurance, and hope to see you soon, somewhere, somehow.
So what was the joke?
Oh. Which joke?
You were writing it from 6 to 7.
Oh, yeah, because I was not counting well. I remember the joke. Did you know that there's 3 kinds of mathematicians? Yeah, those that know how to count and those that know how to count. So that's the joke.